In this section, we're going to look at lenses, and we're going to use an approximation where the thickness of the lens is actually much smaller than the distances between the lens. So all the equations here that you see make that assumption. If you have a thicker lens, then we have to take into account the propagation of the light through the thickness of the lens. So thin lenses, basically, some type of transparent material, glass, plastic. Usually we're dealing with something with an index of refraction around 1.5 up to about 1.8. And obviously we use these lenses to form images by refraction. And most thin lenses use spherical surfaces. However, hyperbolic surfaces actually give a superior image. So here's some different examples of common lenses that we come across. The biconvex lens has both positive surfaces on either side. And when I talk about positive surfaces, a positive surface bows out from the center, okay? It's convex. And that gives you a positive focal length. The plano-convex has a planar side on one side, so there the radius of curvature is infinite. The other side has a positive side. And then meniscus has both a positive and a negative side to it, so convex and concave. However, the convex has a smaller radius of curvature than the concave side. For diverging lenses, biconcave, name's pretty self-explanatory. Both sides have a negative curvature to them, plano-concave, one negative side, one side with a planar surface. Meniscus concave, again, both convex and concave, except for the concave side has a more diverging tendency than the convex side. It has a convergent tendency. So like our spherical mirrors, we define something called the focal length. The focal length is the distance that an image would form if an object were placed at infinity, or if we took parallel rays. This is the point at which the rays would converge. Thin lens has two focal points on either side, since light can travel in either direction. One can think of a convex lens as actually being a collection of different thicknesses of glass or different thicknesses of a high index material. And on the outside, the outermost edge of the glass, we are going to have the smallest amount of delay. And in the center, we have the greatest amount of delay. And what this causes is the wavefronts on the outside to actually get ahead of the wavefronts on the inside, creating converging wavefronts, which correspond to converging rays. And here we can actually see this happening. Again, in the center, we have the greatest distance, so there we have the greatest delay. So the center of the wavefront is going to fall behind the outer edges. And again, this allows us to produce this convergence. If we were to draw the rays here, we would see the rays coming in as parallel. Remember, the rays represent the perpendicular, the normal direction to the wave fronts. And here we can see the rays on the other side converge to a point, which would be the focus. And again, here's just an optical image of, or a physical, image. It's a photograph of parallel rays converging to a point. And again, the focus is on either side. If the light rays are coming from the left, they will converge to a point on the right for a converging lens. If they're coming from the right and traveling to the left, they will converge on the left at the same distance, which is the focal length. Now, how is the focal length of a lens determined? We use something called the lens maker equation to get an approximation of where the focal length is going to be. And it depends on a number of different factors here. First of all, we typically assume that the outside index of refraction is N1, it's air, so it's about 1. N2 represents the index of refraction of the lens itself. Now here, the higher the index of refraction, the more the delay is going to be at the center of the wave compared to the outer edge. And that's going to make this lens more convergent. So make a glass lens out of extra dense flint glass at 1.8 for an index of refraction. That is going to have a shorter focal length. It's going to be more convergent than, say, something made out of crown glass at an index of refraction of 1.52. Besides the index of refraction, also radii will determine how convergent it is. Now we have two radii here. We have R1, which is on the left side, and R2, which is on the right side, okay? R2 is negative here, okay? Because it's on the right side. R1 is positive. So when we plug them into this equation, we have to plug in the proper sign accordingly. So once again, this lens has two convex sides. So both of them would be a positive curvature. Let's use an example here. Here we have our biconvex lens. The first radius is 25 centimeters, the second radius again, since we're coming from the right and defining the radius that way, we make that negative. We plug that into the equation. 1 over 25 centimeters minus negative 1 over 25 centimeters gives me 2 over 25 centimeters. And we multiply that by the ratio of the index of refraction of N2 over N1 minus 1. That gives us the optical power of the lens in inverse centimeters. And then finally, we take the inverse of that, and we get 24 centimeters for this crown glass. Again, crown glass, 1.52 for an index of refraction. We take the air to the index of refraction of 1. Now, simply changing to extra dense flint glass at 1.81, we see that we go from a focal length of 24 centimeters down to a focal length of 15 centimeters. All that's changed here is this right here. Okay, the index of refraction was changed. We went from, again, a index of refraction of 1.52 to an index of refraction of 1.81. And because we're taking the inverse here, a larger index of refraction or larger ratio of index of refraction minus 1 is going to give you a smaller focal length, and that corresponds to a more convergent lens. Remember, smaller numbers here correspond to a more powerful lens, meaning that their ability to change the direction of the rays becomes larger as the focal length becomes smaller. Here's a plano convex lens. Here we're going to leave the same radius of curvature of 25 centimeters on the left, but a plane surface has a radius of curvature of infinity. So when we plug that into this equation right here, 1 over infinity is actually 0. So now we take the focal length, the inverse of the focal length is 0.020324, and we can see that the focal length is larger for the plano convex. It's not as convergent as it was for the biconvex with the same radius of curvature. Again, we're going using extra dense flint glass here with one surface compared to two surfaces. We see that the focal length pretty much doubles. Thinking about this, the first surface, this first interface right here, is going to converge the rays just as much as the second surface is here. So that's why we end up having half the focal length of a biconvex compared to a plano-convex. Okay, here's a meniscus convex lens. Notice we've introduced a new radius of curvature. This is the concave side, and I put that on the left-hand side, so that's going to be a positive number. But the radius of curvature is less for the convex side, making it more powerful or more convergent than the concave side is divergent. And the net result is I still have a positive focal length, albeit very long, 96 centimeters compared to the other distances, but still we have a net positive focal length. And just so you know, I did go back to using crown glass for this example right here. So the focal length depends on essentially the index of refraction of the material and the radius of curvature of the different surfaces. The more convex the surface is, the more convergent the lens becomes. The more concave the surface is, the more divergent it becomes. And we didn't do a calculation with a concave lens, concave or concave plano, but that focal length would be negative if you plug in the correct numbers. So now we want to look at, given a particular object distance, we've basically established that we're going to get some focal length for this particular lens, right? For some object distance, where is the image going to lie and how is it going to be magnified? Well, we can see in this case right here with this ray diagram that the object produces an image which is inverted and slightly smaller. How do I get this ray diagram? Okay. And again, here is the focal length based on the lens itself. We can see how these rays are passing through this. Notice that it's sort of a similar situation that I had with regard to the mirror. We have one of the rays which is going to pass through the focus, then become parallel. Another ray that just passes through the optic axis, undeflected. This one goes parallel and passes through the second focus to form the image. Okay. Now, before we talk about those rays and what the possibility of rays are, we need to talk about magnification. Okay. The magnification, which is the height of the image, the lateral magnification is the height of the image divided by the height of the object, is going to be equal to negative di, the distance to the image, divided by the distance to the object. And what we see here is that these two green triangles are just all the same angles, it's just scaled differently. So basically, this bottom part is DO, here is DI. The ratio of DI to DO is going to be equal to the ratio of HI to HO, okay? Which, of course, is our magnification. So simple geometry demonstrates that the magnification is proportional to the ratio of the distance of the image to the object. Okay, let's do the ray diagram for a thin lens. The first ray is going to be drawn parallel to the principal axis. It's going to pass through the second focal length, and that's going to be this red line right here. Okay, so you see it starts out parallel, then it passes through the focus. Second ray is going to, as we said before, go right through the optical axis. It's going to cross through the center of the lens, and it's not going to change direction at all. The last ray passes through the front focus and then becomes parallel. And we can see that all three rays converge at this point right here. Now again, the three rays are coming from the top of the object. So to reconstruct that, we see where they converge, and they converge right at that point right there. What happens to the image based on where we place the object? What if we place the object well beyond the focus of the lens? Okay, we're going to make the object distance much greater than f in this particular case. Well, as you can see, we've showed this image before using the rays. We get an object which is inverted. We get an object which is smaller. We get an image that's smaller. We get an image that's closer to the lens than the object in this particular case. So plugging in the numbers, here's how I would do that. Now again, I'm assuming that we still have the same lens throughout all of these examples. We're going to set the focal length to 10 centimeters. That'll be the same for everything, except for our divergent lens. We'll use something different there. So focal length of 10 centimeters, I plug that in to my equation. I plug that into F. My object distance is 25 centimeters. I want to solve for DI. So DI is equal to 1/10 minus 1/25. That gives me 0.06 inverse centimeters. I take the inverse of that, and that places the object at 16.7 centimeters. So yeah, the image is closer than the object. So when we do the magnification is less than 1. The absolute value is less than 1. This negative sign indicates that the image is upside down. Okay, let's push the object closer to the focus. Okay, now I'm going to push it a little bit closer. Notice that my image has also become larger. Now, the object distance is approximately twice the focal length. Okay, here we go. I guess I mixed up some of my my slides. Again, focal length of 10 centimeters. We've now pushed this to 20 centimeters. 1/10 minus 1/20 is 1/20. That gives me 0.05. The inverse of that is 20 centimeters. So as you might have guessed, at twice the focal length, our image is still inverted, but it's going to be the same size as the object. Okay, what about the case where we get even closer, less than 2f? Okay, for this case, you're going to get a even larger. I lost a slide here. I lost my slide. Okay, well, you're going to get an even bigger image. And that's unfortunate. But again, you can see that clearly the image is moving farther away as the object is moving closer to F. Now, if you try to put your object at F, you have the same problem that we had with the convex mirror. You're not going to get an image, okay? Getting closer than F. Now, be very careful here, because now here's the object. The image will now flip to the other side. What we see here is the image is flipped to the other side, but it's also become virtual. So basically, when we look at this, okay, here's the focal point right here. Anytime we put an object on this side of the focal point, we're going to get a virtual image. It's going to be right side up. Anytime the object is on this side of the focal point, we get it real, and it's going to be inverted. And again, at F, you can't get an image. In fact, if we make a graph here, and we graph the size of the image, not the magnification, but the size of the image, as a function of position. Okay, we'll do magnification. We'll say that this is the 0 right here. Okay. The magnification does something like this. It goes down and asymptotically blows up, and then at F, it then goes the other way till obviously we can't go any further because we're getting closer to the lens. So here we have a real object less than the focal length, and a virtual image forms. We can only draw 2 of the rays here. That now let's say we say the object distance is 5 centimeters. Plugging this into this equation, unfortunately, I think I messed up here. A few problems with these slides. This should be 6.5, so 6.5 centimeters. I plug that in, and I can see that the image is negative 18.6 centimeters. Okay, so the fact that DI is less than 0 puts it on the left-hand side of the equation. And since the light goes from left to right, okay, this indicates that physically this image is informing. We can't put it projected onto a sheet or projected onto a screen. So yes, it's a virtual image, and it's 1.9 times larger than the original object. So again, this should be 6.5 centimeters here. For a diverging lens, here we have a biconcave lens. The focal length is negative. It's less than 0. And that is because for parallel rays, there's no condition where we're going to focus to a point. Okay? If we put parallel rays through a divergent lens, they're going to diverge. If we trace them back in time, they will come to this virtual focus. But again, this point does not exist. There isn't a point where these rays converge. So what about the ray diagram for a diverging lens? Well, diverging lens makes things appear smaller. So if this is the object right here, and we draw our different rays, we can see this first ray right here, okay, ends up diverging. If we trace it back in time, would have intersected this focus right here. So it agrees with what we have done before. A parallel line, okay, will refract in such a way that it passes through the focus, but the focus is negative here. So we have the focus behind the lens. And then, of course, this one's easy. This one goes through the optical axis at the location of the lens. That just goes through unrefracted, and the intersection of those two gives you the location of the image. So the image here is right side up, but its magnification is less than 1. So let's say I have a biconcave lens. The focus is 10 centimeters from the lens, but it's negative. So the focal length is negative 10 centimeters. We plug it into this equation. We get 1 over negative 10 minus 1 over 22. 22 centimeters is the distance of the I did this backwards. Should have been the distance of the object. And yes, this is DO, this is DI. So there we go. So yes, the object was 22 centimeters away from the lens. Here the image forms negative 6.9 centimeters. And again, here's negative 10, here's negative 6.9. It gives me a virtual image, which is right side up, at a magnification of 0.31. If we have a combination of lenses, the procedure is pretty straightforward. Take the first lens that the light is going to pass through, form an image. We'll call this image 1. Image 1 becomes the object or object 2 to lens 2. You then take that object and form a new image. So for instance, let's say that I have 2 convex lenses and I want to know where the final image is going to form. And again, is your object forms its first image due to this lens right here. Then again, that image is just treated just like it was an object. Focus that, okay, due to the second lens, that produces a new image. We'll call that image 2, okay? And that is essentially the final image that I'm going to see. A little bit sketchy on the rays, I know, but that shows us how an object forms an image, and that subsequent image can be used to form another image. In fact, you can do this with as many lenses as you want. Keep forming successive images. Again, you have to be careful that you go through this lens first to form an image, and then this lens. You can't form an object from the second lens and then use the first lens to form another image. That's not going to work. And as you can see, as I change the position of that second lens, my image changes. So holding things fixed, move the second lens closer, my image gets bigger and it moves further away. If you have a projector, this would be a way of showing, by moving this lens back and forth, how I can focus the light or focus the image at different distances.